day, everyone. This is going to be just a quick little run through of some of the AP Thermo questions. Thermo happens to be something that appears almost every single year on the AP exam. The questions are not difficult. It's just a matter of understanding a lot of times the delta H, because they can give you so many different forms of delta H, and sometimes people just aren't aware and maybe just kind of skim over it thinking they know what that delta H is, and then they make mistakes. Okay, and so I want to make sure that we just kind of go over that a little bit. So when we're looking at delta H, are they all the same? No, they are not. Okay, they're not all the same. So we can have a whole bunch of different delta H's. Now, if they just say simply delta H, what they're probably referring to is delta H of the reaction. Okay, so almost always if they just say plain delta H, they're talking about the reaction's delta H. And this can basically be for any reaction that you want. Okay, so this can be for any reaction. And again, it is going to be the enthalpy change for any reaction. Okay, and remember, what we're talking about here is either the energy that's absorbed or released for that reaction. Okay, now I also want to make sure that I mention that there are different ways to calculate delta H. So the question is, for example, are we calculating it theoretically or are we calculating it experimentally? Okay, experimental is calorimetry for the most part. So you're either using a bomb calorimeter or you're using a simple calorimeter, and then you're going to do delta H equals MCAT. Remember, if you want kilojoules per mole, kilojoules, moles, kilojoules over moles. So remember, MCAT will only give you the kilojoule part of it. You have to solve for moles maybe separately, either by using M times V, molarity times liters, or if you can change grams to moles, if you know what the substance is, then you can do it that way as well. And so don't forget that when you assign a sign, it only goes to delta H. Nothing else has a sign. You do it after the fact. So if you reacted the two substances, for example, together and you saw that the temperature rose, well, then that must have released energy. That means that it's an exothermic reaction. You assign a negative sign, for example. Okay, that's experimental. What if it's theoretical? Okay. Couple different ways for theoretical. One way is using delta H equals products minus reactants. So all you're going to do is you're going to find your delta HF values from a thermo chart, or they'll be given to you. And so then you simply just do the sum of the products minus the sum of the reactants. Remember, I always do this. I find it easier to say add your products, subtract your reactants, don't forget your coefficients, and makes it really easy to do the math. Sometimes you're being asked to solve for one of the substances, the delta HF of one of the substances, so you can do that as well. The other way that you can do it theoretically is if you are given, is by Hess's law. If you are given different intermediate reactions and then you have your target, and your target is the one that you're trying to find the delta H for. So you can manipulate your intermediates to try to match your target. So you can flip them, you can multiply by 2 or divide by 2 or whatever it is. And then once you get it so that it's lined up stoichiometrically, where everything would cancel out except for those items in your target reaction, then you simply add up your delta H values and call it a day. It's pretty easy, okay? So a couple different ways that you can do that. I just wanted to make sure I ran through experimental versus theoretical. So now let's talk about different delta H values. So again, you can have delta H of a reaction. You can also have something like delta HF, like we were talking about the heat of formation. So remember, and this is great to have memorized too. So this is the energy absorbed or released for the formation of 1 mole of a substance from its elements in their standard state. Don't forget that. Elements in their standard states. Elements in their standard states. What does that mean? When you go to the thermo chart, they have to have a value of 0, okay? So it's very easy. If you look at a periodic table, it would be in its natural state as solid, as gas. Remember, the only two that are liquid are mercury and bromine, but bromine is Br2 because it's diatomic, so don't forget that you have to also remember your diatomics, the Brinkelhoffs. Those are the zeros, okay, in their natural state. All right, so that's the heat of formation. We can also have something like delta HCOMB. That would be heat of combustion. You can also have delta HF. That's called the heat of fusion. Heat of fusion, I want to make sure that you remember, this is actually for melting or freezing. Okay, so you can either be melting, going from a solid to a liquid, or a liquid back to a solid. That's what they have as a regular F. Okay, you can have delta H of vaporization. Well, vaporizing is either going from liquid to gas or gas to liquid. Remember, it's the same value, it's just that the sign is going to be different. Okay, and always keep in mind, If a stove helps, I say at the end of my kitchen is a stove. So if a stove helps, then it's endothermic. Because if you're just looking at vaporizing or freezing or melting or condensing, then you don't have a temperature change, okay? So keep that in mind. Instead of doing delta H equals MCAT, that doesn't make sense because your delta T would be equal to 0. You can't multiply or divide or anything with the 0. Instead, what you do is you do a bridge problem, and you can either use the delta HF or the delta H vape problem to be able to solve for that, just like we did on the very first page of the notes at the bottom there. Okay, now there really could be anything delta H. So let's say that something is decomposing. You could even kind of do like a decomposition, for example, of it, okay? So there is also a delta H of dissolution, okay? So dissolution, and maybe they would even write DEC for decomposition, so we like kind of made that different. So dissolution is dissolving something. So you could just simply be putting it in water, and then either just like we did with the hot pack and the cold pack, the temperature can either go up or down and be exothermic or endothermic, okay? So a whole bunch of different delta H's, and so I wanted to make sure, because a lot of times people just see delta H and they automatically think that it's the heat of formation, and so then they're like, oh, I can do products minus reactants with this number. Wrong, okay? So number 1 says, they're giving you different substances. And by the way, this is just a table, kind of a chart, and then you're going to go straight to letter A. So this first part isn't even a question, all right? So they're just giving you some information. And so what they're saying is these are enthalpies of combustion, and notice they're calling them delta H's, okay? But I want to make sure that you're aware of this. This is actually delta H of combustion, which means it is for the burning of that substance. Now, how would you know? Well, carbon in a solid state should have a delta H of 0 then. And H2 gas should also be a 0. And maybe you even remember H2O liquid would be negative 285, something like that. So they're not even putting that down. And by the way, they will not give you a thermo chart. So when you're doing these problems, it's expected that you're not using anything but a periodic table. Okay, so I also wanted to make sure that you are aware of that. Okay, so letter A says, write a separate balanced equation for the combustion of the following. Okay, so we actually have to write 3 separate reactions for each one of these combusting. Okay, what does that mean? That means, for example, that your carbon solid is going to be burning. Okay, burning. Remember, reacting O2 with Cha or Cho always produces Co and Ho. Now, in this situation, can I make CO2 and H2O? Use your common sense. You can't. There's no hydrogen there. It's not a Cha or a Cho. It's just carbon, okay? Now, if you look, it says, consider the only products to be CO2 gas and H2O liquid. But they're not telling you it has to be both. They're just saying that your only products could be that. So if you weren't sure what you were going to get, well, now you know what your product is. It must only be CO2 gas, okay? And so then they also did say to balance it, so just make sure that you end up balancing, which in this case it is balanced, okay? So that's the first step, is to write separate combustion reactions. So you're going to do the same thing for the H2 and the C2H5OH liquid, keeping that in mind, okay? Letter B says, in principle, ethanol can be prepared by the following reaction. Calculate the standard enthalpy change delta H for the preparation of ethanol as shown in the reaction above. What does that mean? Now, if you had a thermo chart, which we don't, you could simply just say products minus reactants. And they obviously don't want you to do that. And the reason why we know is because, so C2H5OH, they're asking us for the preparation of this. And so they're saying as the reaction is shown, and we are making that, so that would make sense. But I don't know. I know what the liquid is, the enthalpy of combustion of it. That's not the delta HF value, okay? So if we looked at a thermo chart and we looked up these values, none of them would be the same. Again, good that you know that this is 0, and good that you know that that one's 0, but again, that's not helping us because we don't even know, they're not telling us water is a liquid, okay? So obviously they want us to do it a different way. What way do they want us to use? Obviously they want us to use Hess's law, okay? So the heat summation one. Okay, so this is my target reaction right here. So what I'm going to do first is I'm going to draw my sum line. So there's my plus sign. And then I always like to line up my arrows, so we'll try our best to get this lined up. So I have 2 carbon solid plus 2H2 gas plus H2O liquid. And then on the right side of my arrow, I have my C2H5OH liquid. Okay, so then I'm going to line up my arrows. I know I have 3 reactions to go. Where are those 3 reactions coming from? Well, letter A. That's why they had you write those 3 reactions out, okay? And so what you're going to want to do is you're going to use your circles, squares, and triangles to figure out which do I need to change any of them. Okay. You have to keep in mind, though, this is important because they're giving you, these values are in kilojoules per mole. Per mole of what? Per mole of any one of these combusting. So it can only be 1 mole of that substance combusting. So you don't even care what the coefficients are on everything else. You just need to make sure that it's for 1 mole of that one. Again, or what you can do is, if it happens to be a coefficient of 2, obviously you could double your delta H value as well, okay? But again, when they say the enthalpy of combustion, this is not the heat of formation. This is so important that you understand this, okay? All right, let's move on to 1995. Now, that was 1998. I know this is a long time ago. But now we're in 1995, and it's exactly the same. And you could go, again, you can go to any year and you'll find a thermal problem, and they're all very similar to each other. So this you're going to see is similar. It says, write the balanced equation for the complete combustion of propane gas, which yields CO2 and H2O. So they're even telling you that it's going to make CO2 and H2O. So you're going to write the reaction. Then they tell you, this one's a little bit different. They tell you that the heat of combustion of propane is negative 2220.1 kilojoules per mole, and they want you to calculate the delta HF of propane given the fact that your HF of water is this number, your HF of CO2 is this number. Okay, now, you also already know, even though they're not telling you, you know that oxygen's value is 0, okay? So if they give you the HF, the heat of formation of water, they give you the heat of formation of CO2, they're giving you the total heat of combustion for the entire reaction. Well, now it's kind of like solving for X. So we had talked about that before. Really important that you know how to do this, by the way, okay? So what you're going to do is you're going to end up solving for X to try to check to see if you can figure out what the delta HF is of propane, okay? So just to kind of give you an idea of what's happening here. So you have your balanced equation. So I'm just going to call this A plus B yields C plus D. That would be like your CO2 and your H2O. And so you already know that the delta H for the entire combustion reaction is equal to that negative 2220.1. They give you the water value. They give you the oxygen and the water value, and you already know what oxygen is when you're reacting with oxygen. So all you're going to do is basically solve for X. You can use products minus reactants. Okay, so pretty easy on that one. Then, again, a little bit of something weird here. It says, assume that all the heat evolved in burning 30 grams of propane is transferred to 8 kilograms of water. And then they're giving us the specific heat. And it says, calculate the increase in the temperature of the water. Okay, obviously, it looks like they want us to use MCAT, okay, which is great. It's awesome to use MCAT, okay? The only thing is, in this problem, is if you go to use delta H equals MCAT, and we know that we're solving for our temperature change, that we're trying to find the increase in temperature. Again, don't worry about increase or decrease because they're just saying the change. They're not saying, like, your water temperature started at 25, what does it end at? They just want delta T, okay? Positive or negative doesn't even matter in this situation here. Okay, the only thing is, if you remember from what I told you, so I see the mass, remember, it's 8 kilograms of water, so I can easily switch that. And by the way, if the substance is reacting in the water, you do want to add the masses together, okay? So keep that in mind. Very important for the lab, by the way, okay, for the enthalpy lab. But if you're using something like propane is burning and it's not necessarily reacting with the water, what's happening is the water is just sensing its energy change. They're two separate things. The burning of the propane is happening differently from the water. Then what you want is you want to make sure that the mass is just the mass of the calorimeter, okay? Not that 30 grams of propane, again, because it's not reacting inside of the water. So I know my mass, they're telling me my specific heat, I'm looking for delta T. The question is, what is the delta H for this reaction? Well, they're telling me that we're burning 30 grams of the propane, okay? Keep this in mind. Now, we know that the combustion of propane from letter B is negative 2220.1 kilojoules for every 1 mole. So what you basically need to do first before you do MCAT, and so don't put the negative 2220 here. That's wrong because we're not burning a mole of it. We're burning 30 grams of it. So think about that for a second. It's, again, like the first page of our notes on the bottom where we were saying, okay, could I figure out the energy if I know the number of grams? Could I figure out the amount of energy that a certain amount of grams will give me for a particular substance? And so that's what you're going to use for that, okay? So that's kind of a big tip on that one. Okay, last one. All right, so again, a little bit of a twist here. So this one's interesting. They give us the reaction, and then it says when a 2-gram sample of phenol, and so they're telling us what phenol is, nice, is completely burned according to the equation above, 64.98 kilojoules of heat is released. Okay, use the information in the table below to answer the questions that follow. Okay, so they are giving us the standard heats of formation. Again, very important that we know what we're being given. In that other problem, we were given the delta H of combustion. So now these are actually delta HF values. So that little like cursive F. And so if you were to do products minus reactants, then you could use all of these values, for example. So the first question says, calculate the molar heat of combustion of phenol in kilojoules per mole at 25 degrees Celsius. Okay, wait a second here. So what they want is, they want this C6H5OH, they want the molar heat of combustion of it. They're not even asking us for the delta HF of it. This is very important. They're asking us for the heat of combustion, okay? Which means, combustion means you're going to burn it. You're going to react it with oxygen, okay? So my recommendation is always like think about, you can write down the equation. We don't know if we even need the equation at this point. We may not even need the equation. If we tried to use the equation, then if we wanted this, we would try to do products minus reactants. The only issue is I don't know the heat of formation of C6H5OH, which means I can't do products minus reactants, okay? So that would be my first thought is let's do products minus reactants and see if I could figure it out, but I can't figure it out. I do know oxygen, obviously, they tell us the oxygen value, we knew that anyway. We know water is a liquid, we know CO2, but we don't know the C6H5OH, okay? All right, so think something else. Well, here's where ratios come in, by the way, okay? Ratios are so very important. It's like bridges, anytime you use bridges, okay? So I know that I want the kilojoule per mole value. They're telling me that when I burn 2 grams, I get 64.98 kilojoules. So if you know that when you burn 2 grams, you get 64.98, could you switch that to figure out how many kilojoules it is if you have a mole of it? So pretty easy, really easy. Again, bridges are going to be super helpful, but I'm not even going to tell you anything else because I think I'm giving you more information than you would even need to be able to solve that, okay? But it's a really easy bridge problem. Okay, letter B. Now it says, calculate the standard heat of formation. They want to know the delta HF of phenol. In other words, they want you to figure this out. Okay, well now, you're basically going to use X just like we talked about before. So it's kind of like the A plus B yields C plus D. So I already know oxygen is a gas. I already know CO2 and water. They gave us both of those values. What we're looking for is this, and I also just figured out the heat of combustion from part A. Okay, so part A's answer, but make sure that your sign is right. Okay, just make sure that you've done that part correctly because that will affect your answer. But again, you're just going to do products minus reactants is equal to delta H. And I did want to go over that with you real quick here, just a second time, just to make sure that you're okay with this. So I'm just going to make up a problem. Let's say that it's 2A plus B yields 2, I don't know, let's make it 3C. Plus D, okay? And let's say that I'm looking for A, all right? So I don't know what A's value is. And B, let's say I look up and it's 20 kilojoules per mole, and C is negative 350 kilojoules per mole, and D is a positive, I don't know, 75.0 kilojoules per mole. Okay, so I just made up these numbers as if I just got them from a chart, all right? And again, this is what I'm calling X. And let's say that I know that my delta H for the entire reaction, I had it figured out, and it was equal to 355 kilojoules per mole, for example. Okay, so what I'm going to do is I'm going to do products minus reactants. So, and I'm going to set it all equal to the 355. So I'm going to say 355 is equal to products. So I would say 3 times negative 350 plus 1 times 75.0 minus my reactant. So I'm going to say minus 2A or 2X if you want, minus 20.0 for B. Okay, don't forget, you have to subtract the reactants, okay? So it's not adding, unless you want to do the sum of first, which in my opinion is annoying, okay? So what I want is, I actually want 2A alone. I want my 2A alone. So what I'm going to do is I'm just going to add it to the other side. So algebra. So I'm going to say plus 2A on this side. So then I have 2A on this side, but then, and that's what I'm looking for, but then I'm going to subtract the 355. So again, just your easy algebra. So minus the 355. Okay, let's plug this into the calculator. You do it with me, and let's see what you end up getting. Did you get that 2A is equal to a negative 1350 kilojoules? But I still need to get rid of the 2, so I'm going to divide by 2 on both sides. And I get that A is equal to a negative 675, and that would be the kilojoules per mole for my substance A. That's actually called my delta HF in that situation then. And so I hope this was helpful to you. Happy day to all of you, and hopefully you can get through these problems pretty easily now.